Welcome to our Quantum Deep Dive, where we explore the cutting edge of technology. Today, we're diving into an insightful essay by Georg O. Schneepadt to get our heads around a really fascinating concept, quantum kernel methods.
Yeah, and it all kind of boils down to this one central question, a question that could totally reshape artificial intelligence as we know it.
Exactly. What if we could give our computers a new, fundamentally more powerful way to see patterns in the world's most complex data? So, to really unpack all of that, we've laid out our explainer in 6 key sections. We're going to build this idea from the ground up. Okay, I'm ready. Let's dive right in, starting with our welcome to the quantum realm.
So at its absolute core, machine learning is just about finding patterns. But an AI's ability to actually find those patterns, it depends completely on how the data is presented to it. That's so true. In fact, the quality of that representation is, a lot of the time, the single biggest factor that determines whether an AI model is going to succeed or just fail. So let's take a look at why that's such a huge challenge in the classical world.
And that brings us to section 2, hitting the classical wall. This is where we're going to dig into why real-world data can get so tangled up and what that means for classical computers. So yeah, let's start with a problem our computers are dealing with every single day. You know, in a perfect world, all of our data would look just like this. Super neat, organized into these distinct groups. An algorithm could just swoop in, draw a line, and say, okay, everything on this side is A, everything on that side is B. Done. Simple. But, as the source material points out, the real world is almost never that clean. I mean, think about things like financial markets, or molecular structures, or even just complex images. The data points are all tangled up, creating these nonlinear patterns that a simple straight line just can't cut through. Right, and to solve this, computer scientists came up with something truly brilliant called the kernel trick. The best way to think about it is like putting on a special pair of 3D glasses. If your data is a tangled mess on a flat piece of paper, the kernel trick kind of lifts it up into a third dimension. And suddenly, those tangled lines aren't tangled anymore, and you can just slide a clean sheet of paper right between them. You've basically made an impossible problem possible. And that classical trick is incredibly powerful, don't get me wrong, but it has its limits. As the essay points out, when you get to extremely high-dimensional data, the method just starts to fall apart. It hits these massive scaling problems and can get really unstable. So when even our best classical tricks fail, what do we do next? And this is where the hero of our story comes in, the quantum kernel. It isn't just another clever math trick. This is a lens that's built from the fundamental laws of physics itself. It's a completely new way of seeing. The difference in scale we're talking about here is, well, it's just mind-boggling. For a classical computer, simulating more dimensions is ridiculously expensive. The resources you need just grow exponentially. But for a quantum system, this massive high-dimensional space, it isn't something it has to build. It's its natural home. Oh, for sure. And what's so wild about this slide is the sheer scale of that natural home. The number of dimensions a quantum computer can play in grows exponentially with every single qubit you add. So with just 50 perfect qubits, you're not working in 50 dimensions. You're working in a space of 2 to the power of 50. That's, over a quadrillion dimensions? It's a space so gigantic no classical computer could ever hope to simulate it.
So here's the crucial point. A quantum kernel uses these unique quantum properties, things like interference and entanglement, to map our messy classical data into that enormous feature space. And once it's there, it can find hidden relationships and calculate similarities in ways that were just impossible before. It starts to reveal patterns that were totally invisible to our classical tools.
Okay, so how does this actually work in practice? Well, it's not a purely quantum process, which is actually what makes it so exciting for the hardware we have today. It's a really clever hybrid approach that literally combines the best of both worlds. Right, so first things first, you have to translate your classical data, we're talking image pixels, stock market numbers, whatever, into a language that qubits can understand. The source material talks about a few ways to do this, but a really popular one for today's hardware is angle encoding. You literally turn the features of your data into the rotation angles of quantum gates. It's practical and pretty robust, which is absolutely key for the noisy quantum computers we're working with right now. And this slide just illustrates the entire workflow beautifully. The quantum computer does the really hard part. It encodes the data, runs it through a quantum circuit to transform it, and then calculates the similarity between all the data points in that massive quantum space.
This spits out something called a kernel matrix, basically a grid of similarity scores. And then this matrix gets handed back to a classical computer, which uses a powerful, well-understood algorithm like a support vector machine to do the final learning and classification. It's such a cool partnership.
Okay, that brings us to section 5, promise, peril, and practice. This is where we look at the incredible real-world applications of this tech, but we also get real about the hurdles we're still facing today. And one of the most direct, most promising applications of this whole technique is the quantum support vector machine, or QSVM. It's a perfect example of that hybrid approach we were just talking about. You take the robust, proven framework of a classical SVM and just supercharge its ability to see patterns by swapping out the classical kernel for a quantum one. And this slide, well, this is our reality check. The potential in fields like molecular analysis, drug discovery, finance, it's just huge. But we are still very much in what's called the noisy intermediate scale quantum, or NISQ era. And what that means is that today's quantum hardware makes mistakes. Noise and decoherence, which is where these delicate quantum states just kind of fall apart, are major challenges that can mess up the calculations and affect the final result. But the good news is that researchers are not working in a vacuum here. There's this rich ecosystem of both hardware and software that's growing incredibly fast to tackle these problems. We have gate-based quantum computers from companies like IBM and IonQ, and these amazing open-source software frameworks like Qiskit and Pennylane that make it possible for people to actually build and test these QSVMs right now. All right, and that brings us to our final section. The future is transformed. So let's zoom out. What's the really big picture here? Beyond just a better algorithm, where is all this actually heading? This quote, which we've adapted from the conclusion of Schneppat's essay, just captures the grand vision perfectly. We're not just building a better tool for a specific task. We're building a new foundational piece of infrastructure for intelligence itself. Quantum kernels could literally become this universal bridge, translating the messy physics of raw data into the structured language that high-level AI understands. So the crucial point to take away from all this is that quantum kernel methods offer a profoundly new way to see and understand data. By harnessing the strange and powerful rules of quantum mechanics, we might just be able to uncover patterns in the universe that have always been there, but were completely hidden from our classical view. And with that thought, we want to thank you for joining this deep dive, which was based on the insightful work of Jörg O. Schneppat. For sure. For more information and to read the source material for yourself, you can visit schneppat.de. Goodbye for now.
Schneppat.de is a private project by Jörg O. Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.